Hello and welcome to this section of the Physics 3 tutor. In this section we're going to expand our knowledge a little bit and begin to talk about what happens if you have a wire carrying an electric current and you place that wire into a magnetic field. What's going to happen? And I'll tell you the punchline if you think about it. We already know that if we have a magnetic field and we shoot particles or some kind of charged particles, electrons or something, into the field, the force that's exerted is going to be force is equal to Q times V cross B. It's a cross product. It's going to curve that electron in a sort of an arc, and if there's a field there that's uniform, it'll just orbit around and around and around. Now think about what is a wire carrying electricity. A wire is billions of electrons flowing through the wire, so lots and lots of moving particles. So it would make sense that if we take a wire and place it into a magnetic field and then turn the current on in that wire, it would make sense that the magnetic field would exert a force on all of the little charged particles moving in that wire, and thus the force would be exerted on the wire itself. And that's exactly what happens. If you take a magnetic field and you've got it on, and then you place a wire in it, it's hooked up to a circuit, and you turn the electricity on in that wire, the wire will physically begin to move. It'll be pushed by the magnetic field. And so that's what we're going to learn about here. What does that force look like and all of that? So what I'm going to do here is I think what I'm going to do is give you the punchline first. I'm going to draw a quick diagram and show you what the force and what the equation is that describes the force on a charge, I should say a force on a current carrying wire, which is really what the title of the section is. And so you'll have it, right, and sort of in the forefront of your brain. And then I'm going to break with tradition a little bit and I'm going to derive it for you. Sometimes in physics, I think it's better just to present the formula and tell you to use it, because sometimes doing all the derivations for everything just kind of like derails us a little bit too much. But in this case, since we already have discussed in the last section exactly why the force arises on a particle, then it really becomes nice to do this derivation because it follows directly from it and it gives you practice in doing that logical thinking and logical derivations that you see all the time in your physics books. And let's face it, a lot of us, when we read those derivations in those physics books for the first time, you may not get it, you may get lost. How did they do that? So I'd like to kind of present that for you. But before you actually derive anything, I want to give you the punchline because that way you'll know where we're going. So if we have, let me draw a quick magnetic field on the board. This is our magnetic field. It's coming toward you out of the board. I'm trying to draw these little dots as fast as I can. So here's a bunch of dots. It's uniform. It goes on and on everywhere, but I'm just drawing a little bit of it here. All right, now, this magnetic field is coming from me to you. Now, inside of this guy is a segment of a wire, like this. Like that, let's say. Now, this wire might be connected to, some battery here or something, some kind of voltage source or whatever. It's pushing electricity, down that guy. All right. Now let's say, let me change this around for the sake of argument. So we have current coming out of the bottom and going through like this. So I just wanted to label it like that. So the current, if I had to label it, is going this direction. Current is always labeled I. So the current is coming this way, is going through the wire, current is going back to the source. Now it's important for me to say, and we talked about this several sections ago, when we talk about electric current, when we talk about circuits and in physics and in electrical engineering and other things, we're always talking about positive charges moving. So when I draw this arrow, I'm talking about positive charges moving. But we know that in real circuits, in real wires, in real batteries, the positive charges don't move because those are in the nucleus. We know that the negative electrons really are the things that are jumping around from atom to atom and moving through the circuit. So in this circuit, the electrons really would be coming from the negative terminal and going this direction around opposite, right? But the negative electrons would be going opposite of the blue arrow, but they're also negative charge. So don't get too worried about the fact that in real life, the electrons are going opposite here. We've done all this work for you. It turns out that if you have a real life circuit with electrons going one way, of course those electrons are negative charge, right? It's mathematically exactly the same as talking about a fictitious positive current going in the other direction. And I've talked about this at great length several sections ago when we talked about electric current. So for the purposes of every circuit you ever see in a physics course or in an engineering course or anything, you're going to see the current labeled, but it's always in terms of these positive charges moving, even though they really don't move in real life. The negative charges really go the other direction, but they're negative. So mathematically, we talk about positive charge. So I just wanted to kind of get that out of the way because we're going to be talking about this current, and I don't want you to get confused and think about, oh, I have to go negative or change it around. No, 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 no. It's labeled this way. This is called a positive current. This is what we use in our calculations. And if you do all the calculations in terms of electrons that are negative and going the other way, you'll get exactly the same answers for every equation we use. That's why we use positive current. All right, so we have this guy going like this. Now, if you think about it for a second, this current consists of positive charges, because this is positive current, let's say, and it's going this direction, and this magnetic field is coming out of the board. So if it was just one single proton, positive charge moving, the way you would figure out the force on it is you would go Q, V cross B. V is here, crossed with B would mean a force would act this direction. But here, there's not one proton moving, there's billions and millions of positive charges moving through this wire. So because of that, the force on this wire is pointed this direction. Everywhere. It's a uniform force because everywhere this magnetic field is uniform. Everywhere there are positive charges moving this direction. So there's a cross product at every single point in this wire, pushing the wire basically that direction. So if you actually did this in the lab and you flip the switch and turn this current on, the wire would begin to slide to the right. It would begin to slide from the right. It's not magic. It's coming from, that energy is coming from the energy of the magnetic field. It's not that, and by the way, in these little thought experiments, I say, oh yeah, there's a magnetic field that pops up. Well, you're not getting free energy. In real life, you have to generate that magnetic field some kind of way if you really wanted to do this. So, the energy is not just coming out of thin air. It's coming from and transferred from the magnetic field into the motion of this guy right there. All right. So conceptually speaking, you can understand why the force is pointed this direction. Now let me kind of cut to the chase and tell you, since I've kind of drawn it, that the force on this wire, I'll call it FB just like we've been doing before, instead of QV cross B for a single particle, it's going to be IL cross B. This is the main formula. This is the main equation, I should say. So think about it this way. In the other sections, for an individual particle, we said that F is equal to QV cross B. Well, it's crossed with B. That's exactly the same. V was the velocity of the particles, and Q is the charge. Here, I is the charges, right? So that's kind of like the flow of charges. L vector is basically the length of this wire. So let me draw that real quick. This wire has a length L. So this is a length L, and when we put a vector on it, it just means it's the length of this wire in the direction of the current flow. So when you think about it, that's exactly the cross product I just did with my fingers. L vector is pointed in the direction of the wire, and it is the magnitude that has the length of the wire. So when I cross it with B, I cross it this direction, and it's multiplied, of course, times the value of the current that's out in front. So these two equations look remarkably similar, I guess, is really what I wanted to point out for you. For an individual particle, it's the charge in the particle, velocity of the particle, crossed with the field. Here, it's the flow of the particles times basically the direction of motion, because this is the wire direction, crossed with B. So that's very easy to remember. If you don't remember anything else from this section, I'm going to derive it in a second. If you don't remember anything else, then just remember that they're very similar. And so that should help you. And so because of this guy right here, then it should come as no surprise that if you didn't care about the vector part of it, then FB, the magnitude of this force, would be I times L times B times the sine of the angle between them, just as it was for this case. This is just, vector math here. Anytime you have a cross product, the magnitude of the answer is going to be magnitude of L times magnitude of B times the sine of the angle between them. This guy just stays out in front. So this is a direct parallel also from what we had here, because over here we said for an individual particle, magnitude of F is equal to QVB sine of the angle between them. And then finally, If the angle is actually 90 degrees, which is exactly how I have it drawn in this picture, the angle between L and the magnetic field is actually already 90 degrees, then the magnitude of the magnetic field is just ILB. And I'll just put over here for 90 degrees, because sine of 90 is 1. And this exactly follows from what we talked about before. The magnitude here was QVB if the angle was 90 degrees. So I'll put 90 degrees. So really, the granddaddy equation is the true cross product. This gives you everything. If you don't care about the directions of everything, you just want the magnitude, you can drop everything, take the sine of the angle between them, and that gives you the answer. If you know the angle is 90 degrees, then bam, this is very simple. And this will get you by through a lot of problems on your exams, because on a lot of problems, like in my drawing, I have the wire already perpendicular to the magnetic field. So this is the punchline. Now what I would like to do now is derive this for you. I mean, it kind of makes sense from a parallel, discussion that that's true, but I'd like to derive it for you, just to kind of show you where it comes from a more fundamental level. That's going to do two things for you. It's going to let you be prepared if your teacher actually asks you to derive this on a test, because it's possible, believe me, that you might be asked to derive it. And number two, even if you're not asked to derive it on a test, it's get your brain working in terms of physics and how to set problems up. And that's going to help you in all of your future problems. So try not to think of this as being too much of an academic thing. It really can help you. Believe me, if I didn't think that it would help you, I wouldn't include it here in the lecture. So what we want to do is kind of blow up this wire so we can see what's really going on. So first, let me draw a big magnetic field. You have to bear with me. All these dots, these are magnetic field coming right out of the board toward you. I don't like these dots here, so I'll make new ones. All right, so uniform, even though it doesn't quite draw in uniform, it's totally uniform. Now immersed in this, let me kind of lay my wire on the side. I have a wire that's kind of going through here, immersed in this guy. I'm gonna put a little jagged edge here and a jagged edge here. The wire may go on forever and be connected to a circuit or something down there, but at least a portion of this wire is inside the magnetic field. Now, the portion of wire that actually lies inside of the field has a length, L, like this. So the only part that we really care about is the part of the wire that lies within the magnetic field. Whatever length lies in the field is the only part that's going to have a force pushing on it. That length is what we call L. Now, this wire, obviously, is immersed in a field, and it's got billions and billions of charge carriers that are moving around. So let's just pick one. I'll just put a big blue dot here and say it's moving this direction, VD. The reason I'm calling it VD is because when you talk about conductors and electrons or something in a conductor, or charge carriers in a conductor, you usually talk about the drift speed. So this is the speed that these guys are drifting down because of the circuit that you have it in. It's the speed at which they're moving, basically. So don't worry about the D. It's just the speed that these guys are moving. Now, again, we're talking about the positive charge is moving, even though in real life the negative electrons are going the same way. But we're going to save ourselves some headache. Now, because I have it labeled this way, then I can say with certainty, let me go ahead and take these off the top so I have some space here, that the current is really going that direction, because obviously my charge carriers are flowing that direction. Now, if you think about it for a second, if this is the velocity and they're positive charges, and this is the magnetic field coming out of the board, then if I do V cross B, if I go back to the basic formula, V cross B for the force, cross into V, into B, like this, if this is the magnetic field, the force is pushing down. So really, the force on this wire is really pushing down. And of course, it's pushing everywhere that these guys are in here. So this is a diagram. You can use thought experiments to figure out where the force is going to be, but we need to use a rigorous way to really figure out how and what the equation for this force is really going to be. So what we start with is what we know. We know the force on an individual charge. So we'll say F is equal to QV cross B. That's where we start from. Usually when you derive anything in physics, you start with a known. You might start with the equations of motion, or you might start with energy or something and try to work your way into more complicated things like relativity theory or something. Here we know and we claim that this is fact, and now we're going to apply it to a situation. So we start with this fact, all right? So really what we have is slightly different than the case of the individual particle. This applies to one charge. Here, we're not interested in one charge. We're interested in all of these charges that are in between this region that are all kind of drifting and moving this direction through the wire in this region L, okay? So really what we need to do first, if we're going to use this equation, is figure out what charge really is in this region. How much charge is here? Obviously, if I had one particle in there, I would know what the charge is. But I don't have one particle. I have lots and lots of particles that all exist in this little sort of volume of wire here. And in a certain amount of time, basically I'm going to like click a stopwatch and I'm going to watch them drift. And all of these particles that are in this region, I'm going to watch them all drift out of that region. And that amount of charge that's in here is going to go into this equation as Q. That's going to be the amount of charge that I care about, is what is in this length L. All right? So I'm going to basically try to figure that out. So to do that, let's go off to the side here and figure that out. What will Q equal? What is the amount of charge tied up in this region here? Okay? Well, we know that there's a current. Let me write the punchline down and show you why it's true. It's going to be the current times L over VD. Let me show you why this is the case. This current is coulombs per second. That's the unit here. Coulombs per second. This is how much at any given time through any given like plane here, how many coulombs per second are moving through a plane. The unit is coulombs per second, right? Here, length is meters, velocity is meters per second. So this, when you really do it, when you flip this over and cancel your meters and your meters, then what you're going to have is seconds. So what I really have from this little thought experiment I'm doing on the right-hand side is I'm going to have coulombs per second times second, which is going to be coulombs. Coulombs is a unit of charge. A lot of times when you're doing derivations, to be honest with you, you use dimensional analysis like this to figure out what makes sense. We're trying to find out what unit of charge is really in this body that's flowing out because the current is going out. We know that we have so much current. We know the unit of current is coulomb per second that's moving. We know this represents basically how long it takes this body of charge to move out. This is a unit of time, L over V. Think about anything. Velocity is distance over time, right? Velocity is distance over time. Let me write that down real quick. Velocity of anything is distance over time. If I want to find out how long it takes, then I just rearrange and I say time is equal to velocity over, actually what I do is I move this guy over here. Time is equal to distance over velocity. This is distance over velocity, same as this. What I'm trying to find out is, okay, this is how many coulombs per second is flowing in this wire. This is how long it takes this entire volume of charge to move out of the way. So multiplying those two things together, this is how many coulombs flow every second. This is how many seconds it takes to flush this volume out. Multiplying the two things together tells me how many coulombs has flowed out of that region. That's what we're after. We're trying to figure out how many coulombs have left this volume, because that's going to be the charge that's acting by the magnetic field that's pushing on it. All right, so hopefully that's clear. What we do next is basically plug that in. This was the hardest part of the problem, to be honest with you. So the next thing we do is we say F is equal to Q. We know what Q is, I times L over VD, right? Times, now we have V cross B. V is just the velocity of the particles, which is, we're labeling in this drawing, VD, crossed with the magnetic field B. So we cancel the velocity with the velocity, and so the force acting is I, L, cross B. And of course, when you look back at this, you realize that this L really needs to be an L vector because you're crossing it with the magnetic field. So it's really the length of L, which is what we had here. Vector quantity means that it's being a vector that's being crossed into it, and that's how we get to a vector state there. And then this is really the answer, and then we know from before that if we're looking at the magnitude, this is going to be I, L, B times the sine of phi, like that, the sine of the angle between them. And that, my friends, is the derivation of how it works. We basically start from a diagram. A good derivation always starts with a diagram. We have a wire that has a certain physical, volume to it, and it's immersed in a magnetic field. right? And what we want to do is use this equation that acts on each individual particle and kind of apply it to the whole thing. So instead of a single charge, it's acting to a body of charge that's in this wire. Now, of course, it's flowing, it's a current. So this body of charge is flushed out of this volume region, you know, periodically because it's all moving. So we need to figure out like how much charge is really in here. So what we do is we figure out, well, how much charge is flowing per second times how long does it take this volume to kind of scoot out of the way. Multiplying those two things, charge per unit time times the time it takes, is going to give us the total charge. The only thing really tricky about it was basically realizing that this time here, just like velocity is distance over time, time is distance over velocity. The time it takes to flush this stuff out of there is the distance divided by the velocity. So we write it like this. The units all cancel. That we have a coulomb as the final result. And the other thing nice that happens is once we put it in there, this V cancels with this V. So then we are ending up with IL cross B. So now you know if you have a magnetic field and you have a wire with a current flowing through it, basically you treat it almost the same. As far as the right-hand rule goes, you treat it exactly the same way. You look at the velocity of the particles through the wire, you cut through them like a IL. L is in the direction of the current flow through the wire, crossed with B. That's going to give you your force. And of course, if you don't care about the direction, you just do IL, which is just the length of the wire, times B times the sine of theta. I hope that's clear for you. I hope the derivation is clear. If the derivation is not clear, then this is really the equation that you use, either one of these depending on your problem, for all the subsequent problems. So now what I'd like to do is go on into the next section and apply this to some practical problems to show you how it really works.